Hello everyone, Dr. Chang here. We're going to discuss conservation of mechanical energy in this video. Now to discuss conservation of mechanical energy, we need to introduce the difference between conservative force and non-conservative force. What's the difference? Let's look at those two examples. So we have athlete. So the athlete can dive from the board to the water. The gravity is going to do work for this pass. Let's call it pass 1. And then the athlete can also take a slide to the water. Let's call it pass 2. And for the work done by gravity, the work done by gravity in these two different passes would be the same. So work done by G and work done by G in those two scenarios is equal. This is for gravity. So gravity is a conservative force because the work done by gravity only depends on the starting position and end position, starting position and end position independent of the path objective. Now let's look at friction. We can move the book from A to D, just from A to D directly. But we can also move the book from A to B, then to C to D. So we call this one pass 1. We call this one pass 2. Now, for pass 1 and pass 2, the work done by friction apparently are going to be different. The work done by friction along different passes are different. So we'll call friction a non-conservative force. So let's try to summarize. Conservative force is a force that the work done by the force. The work done by the force is independent of the path took. So apparently the definition of non-conservative force is the work done by this force depends on the path that the object took. Now there are two different equivalent way of making a statement of what is a conservative force. Either independent of a path between 2 points, or the work done is 0. If it's starting from this point and it goes back to this point. And this is the property for the conservative force. For conservative force, we can define a potential energy. And that's what we want to discuss. So what are conservative force? So basically in physics 1, we focus on gravity and the spring force. Those are two conservative forces we're going to learn in physics 1. After we move on to physics 2, we're going to learn that the electromagnetic forces are also conservative force. Basically, all other types of forces we learn in physics 1 are non-conservative force. Friction, normal force, tension, the force applied by you, those are non-conservative force. In physics 1, the two types of conservative force we learn are gravity and the spring force. We'll try to discuss gravity first, and we want to introduce conservation of mechanical energy. So we have work and energy theorem, right? The net force done on the object equals the change of kinetic energy. Now we learn the two types of forces. So we see the total net work. We can differentiate them by the work done by non-conservative force and the work done by conservative force. And the work done by non-conservative force would equals to negative of work done by conservative force plus change of kinetic energy. Okay, so work done by non-conservative force is change of work done by conservative force plus change of kinetic energy, which is final kinetic energy subtract the initial kinetic energy. So we're going to relate the work done by conservative force to energy as well. So as we said, let's start with gravitational potential energy. What is the potential energy for gravitational force? If we have a physics book, start from position y1, drop to position yf. What is work done by gravity in this case? We know the definition: work done by a force is force times displacement times cosine theta. Now in this case, mg is pointing down, displacement pointing down, so they are pointing in the same direction. Angle between force and displacement 0. This is a 0. Force is mg. Displacement is y subtract yf. Okay, so the work done by gravity in this case is negative mg displacement. Now we know the total work, the work done by non-conservative force, the work done by conservative force in this case is the work done by gravity equals the change of kinetic energy. And now we also know the work done by gravity is this. The work done by gravity is negative mg bracket yf subtract yi equals delta ke. Now this makes sense because we know gravity is doing positive work in this case. And this is a positive number. This is a negative number. Negative make it a positive number. And the work done by gravity is positive in this case. So the total work done by non-conservative force is change of kinetic energy. Now, if we can define this as change of potential energy, then we can arrive at a conserved quantity throughout the process. Let's see how we can define it. So we can define gravitational potential energy to be mgy. Then mgyf is the final potential energy of the object. Mgy initial potential energy of the object. Okay. So this is how we define gravitational potential energy. Mg times h. H is the height of the object. This is how we define gravitational potential energy. In the work done by gravity. Work done by gravity, this is from our calculation, right? And we define this is PEF. This is PEI. So apparently, like this is our change of potential energy. So work done by gravity, I can write it here. Work done by gravity is negative of change of potential energy. Okay, so we can go back to the very beginning. So we know non-conservative force. The work done by non-conservative force plus work done by conservative force give us work done by net force equals change of Ke. So work done by non-conservative force equals delta Ke subtract Wc and negative of work done by conservative force. So you can also put a negative here. Actually, the negative of work done by gravity is change of potential energy. See, this is change of potential energy. And we also verified by plugging the mgh for potential energy as well. So arrived at this conclusion. The work done by non-conservative force. This is the work done by non-conservative force equals the change of potential energy plus change of potential energy. And we can rearrange it, right? We can put all the final energy together. Final kinetic energy plus final potential energy. Subtract initial kinetic energy plus initial potential energy equals the work done by non-conservative force. Okay. So things will become very, very interesting. What's going to happen if there is no non-conservative force doing work? If there is no non-conservative force doing work, then if the work done by non-conservative force equals 0, then we have change of kinetic energy plus change of potential energy equals 0. Change of kinetic energy plus change of potential, this always equals 0. Then we put final energy on one side and initial energy on one side. So we say Ke plus Pe equals each other always. So Ke plus Pe is a conserved quantity. So the sum of kinetic energy and the gravitational potential energy is a constant of all time. It's a constant of all time. That's why we call it a conserved quantity. So we arrive at conservation of mechanical energy. Now, if all those derivations confused you, don't worry. Just pay attention to this. Just try to understand the following statement. This is a principle of conservation of mechanical energy. First, we define mechanical energy as kinetic energy plus potential energy. The mechanical energy of the object remains constant as the object moves if the net work done by external non-conservative force is 0. So there's another way to make this statement. If only conservative force do work to the object, there is no non-conservative force do work to the object. Only conservative force do work to the object. The mechanical energy is conserved, and the mechanical energy is kinetic energy plus potential energy. It's coming from this work done by non-conservative force equals change of kinetic energy plus change of potential energy, as we discussed. Now, if the work done by non-conservative force is 0, then this has to add up to 0, and we just keep final kinetic energy and the final potential energy on this side. We can move initial kinetic energy, initial potential energy to the other side, so we arrive at this conclusion. Final mechanical energy equals initial mechanical energy. But there is a condition. The condition is the work done by non-conservative force is 0. The mechanical energy is conserved. Yeah. So try to understand this statement. If the only conservative force do work to the object, there is no non-conservative force to work to the object, the mechanical energy is conserved. And for gravitational potential energy, where you choose it to be 0 doesn't matter too much. The only thing that matters is the change of potential energy. So it doesn't matter you choose here to be 0, here to be 0, here to be 0. if the book moves, for example, from here to the table, the change of potential energy would be the same. It doesn't matter where you choose it to be zero. So don't worry about your choice of zero for potential energy too much. It's really the change of potential energy that matters. Let's try to think about this conceptual problem. So we have a ball, we have 3 balls throw from the building. We throw it at the same speed, just a different velocity. Question is, if we can ignore air resistance, what will be the speed of the 1, 2, 3 ball when it gets to the ground? What speed of the ball? Now, we'll give you this quiz immediately after we introduce conservation of mechanical energy, right? So there got to be some relation between that. Let's solve this problem by applying the principle of conservation of mechanical energy. Mechanical energy says initial mechanical energy equals final mechanical energy. Okay, initial mechanical energy 1/2 mvi squared mgyi 1/2, and final mechanical 1/2 mvf squared mgyf. What does it tell us? They start from the same speed, right? So vi is the same for all of them. The speed is the same for all of them. So same for 1, 2, 3. Initial potential is the same for 1, 2, 3. And they all get to the ground. So final potential energy is the same for 1, 2, 3. Now, and we have an equation. So the final kinetic energy has to be the same for 1, 2, 3. Now, if the kinetic energy of the ball for 1, 2, 3 are the same, so Vf is the same. The final speed is the same. And that's what is asked. So the answer should be 4. Yeah, the final velocity of the ball are all the same for 1, for 1, for 2, for 3. So this is how we solve conservation of mechanical energy problem. First of all, we need to define the system. We need to choose a location to be y equals 0. And as we discussed, it doesn't really matter where you choose it. What really matters is the change. So you can choose anywhere you like. Now, apparently, we want to choose it so our calculation is easier. Then select the object that you're interested in, and you find is initial state and final state, initial position, final position, right? Write down the conservation of energy equation, the mechanics conservation equation, and identify the unknown quantities and solve it. So, example, we have a gymnast trampoline. The initial height 1.2 reach a maximum height 4.8 before falling back. What's the initial speed of gymnast? So we just need to build a conservation equation. The work done by gravity equals change of kinetic energy. Or in other words, we can also write initial. So if we replace this, we can also immediately find out it should be initial gravitational potential energy plus initial kinetic energy equals final gravitational potential energy plus final kinetic energy. Now we know at the highest point, maximum height, kinetic energy, final kinetic energy is 0. So this is equation for mechanical energy conservation. PI plus KI equals PF plus KF. Now if we arrange those three terms, we will have this equation. Now we know H0, we know HF. We don't need to even to know M. We know G, we know V0. But we don't know V0, so we just solve for V0, initial velocity. We just solve for initial velocity from this equation. Plugging all the numbers, G is 9.8, initial height 1.2, final height 4.8, so the initial velocity is 8.4 meters per second. Another example. A motorcyclist trying to leap across a canyon by driving horizontally off a cliff. Its initial speed is 38, and the velocity is pointing horizontally. Ignore air resistance. Find the speed with which the cycle strikes the ground on the other side. So first we have to think, can we use conservation of mechanical energy to solve this problem? Ignore air resistance. What are the forces acting on the cyclist when it's in the air? Gravity, right? And gravity is a conservative force. So during this process, the only force doing work to the cyclist is gravity, and the gravity is a conservative force. So mechanical energy conservation checked. So ME conserved. Check. So we build our equation. We build our conservation of mechanical energy equation. Final mechanical energy equals initial mechanical energy. Final mechanical PEF plus KEF, P0 plus K0. Every term has M, so M cancels. So what are the quantities that we already know? We know initial velocity. We know initial height. We of course know G. We know G. We know the final height. We want to find out final velocity. So we just solve final velocity from this equation. So we move everything to the, not the final velocity, to this side, right? And then these two terms combine to this term, then multiply everything by 2. So that's a solution. That's the final velocity in terms of initial height, final height, and initial velocity. Now we just solve it. We just solve it. Plugging all the numbers, we found the speed of the motorcycle is 46.2 meters per second. Now we can use this to solve a large class of problem, conservation of mechanical. So for example, a boy swing down the swimming hole. So in this case, as he is swimming down, what are the forces acting on him? So we have tension, right? We have tension acting on him all the time. We have gravity. And we of course know gravity is a conservative force, so conservative force doing work. T is not conservative force. T, non-conservative force. The question is, does tension do any work to this ball? Now the question is no. Tension doesn't do work to the ball in this case. Why is that? And we know that's the velocity of this ball always. And at any place, t is perpendicular to the instantaneous velocity. So perpendicular to the displacement at that moment. And when T, work done by T is T times displacement times angle between T and S, and angle between T and S is always, angle between T and S is always 90 degrees. Cosine 90 degrees give us 0, so the work done by T is 0. The T doesn't do work. The only force to work is gravity, which is a conservative force. Non-conservative force, T doesn't do work. No air resistance, so air resistance doesn't do work. When only gravity is doing work to the ball, so mechanical energy is conserved. So we can use conservation of mechanical energy principle to solve this problem.